Hi everyone. So for today, I'm going to have you follow along while I do the notes for lesson 3-6, which is parallel and perpendicular lines. And then tomorrow during our virtual period, we will go over the notes and do some practice questions. Okay, so to start, we're just going to look at this very basic diagram right here. And it basically has some streets: Oak, Schoolhouse Road, and Court Road. And I'm asking you, what conjecture, right, or what hypothesis can you make about Oak Street and Court Road? So Oak Street, which is right here, right, Oak, and Court Road right there. So what could you tell me about Oak and Court Road? And if you take a look and you're just kind of looking, they both look like they are horizontal roads. Kind of talked about this last week. And since they both look like they're horizontal roads, something that we can then say is that these two roads are parallel. Now, if you notice something else, it actually looks like Oak and Court are both perpendicular to this road right here. Right? And if you continue down, they also look like they're perpendicular to this road over here. And that's what we're going to begin to look at today. Roads can be parallel, lines also can be parallel, but they can also be parallel to each other but perpendicular to a third line, or in this case, road. So a couple things we're going to do first is just relate two lines to a third line. So take a look at this first theorem. Okay, so this theorem down here says, if two lines are parallel to the same line, then they are parallel to each other. And this is kind of like, I think I've talked about this in class, kind of talking about like heights. So for instance, I'll use some people in class. If Devin and Anthony are the same height, and then Anthony and Logan are the same height, I can say that Devin and Logan are the same height, right? Because since both boys, Devin and Logan, were the same height to Anthony, they must be the same height to each other. And if you look at it over here, I like to look at just this here, the symbol notation. This says that A is parallel to B and B is parallel to C. Notice how they're both parallel to B. That then means that A would be parallel to C. Right? So I kind of like to think of it like this. So since A and B are both parallel to C, A and B are parallel to each other. Okay, so since A and B are both parallel to C, A and B are parallel to each other. Okay, then we can kind of take a look at another theorem, 3-9. So for 3-9, this theorem says, in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So this kind of goes back to before we talked about like with the roads, right? So if you take a look, M and N here, this line and this line, are both perpendicular to T, so they must be parallel to each other. I also like to think about this in terms of the ceiling and the floor. The ceiling and the floor are both perpendicular to the wall. Therefore, the ceiling and the floor are parallel to each other. I kind of think of that in terms of like a room, right? The ceiling and the floor are perpendicular to the wall. Therefore, the ceiling and the floor are parallel to each other. So again, you can kind of like write, since M and N are both perpendicular to T, M and N are parallel to each other. Okay. So again, talking about relating two lines to a third line, where the relating lines are both parallel and perpendicular. Okay, now we can actually prove this theorem, and I'm going to show you how down here. And remember, you guys can pause, make sure you just have all these notes down. So here's how we prove this. How do you prove that the theorem that if R and S are both perpendicular to T, then they actually are parallel to each other? So think about this, right? If I'm trying to prove that these are parallel, well, think about when we dealt with parallel lines cut by transversal. And that's kind of like what this is over here, right? These are my two lines, and then T is the transversal. What kind of angles am I marking here and here? We said those types of angles are called corresponding angles. And we said corresponding angles are equal. Well, corresponding angles are equal only when the lines are parallel. So if you look here, we have corresponding angles. And are they equal? Well, yeah, because both these angles are 90 degrees. So we know all right angles are congruent. Since all right angles are congruent, we know the corresponding angles are congruent. And if the corresponding angles are congruent, then the lines must be parallel. So let's kind of write that down. So since the corresponding angles are congruent, the lines are parallel. And you know that the corresponding angles are congruent because they're both right angles. And all right angles are congruent. And that's key there, right? That's how we know they're right angles, because they have that little box. Okay, so now let's see if we can kind of take this whole idea and turn this into like a question, right? How can we take this idea of like lines being perpendicular and parallel, turn this into like a real life application? So let's look over here. Okay, so a carpenter plans to install molding on the sides and the top of a doorway. The carpenter cuts the ends of the top piece and one end of each of the side pieces at 45 degrees, as shown over here. Will the side pieces of the molding be parallel? And explain. So we want to know, will this piece and this piece, will they be parallel? So think about it. Once I attach the molding, right, so it kind of looks something like this. So right now, I'm going to do my best to draw this. Something like this for the top. And then we have like this is the side and this is the side. So are they going to be parallel? And you're probably thinking, well, I mean, yeah, right? Most of our houses have molding around the doorways and they happen to be parallel. 45, 45, 45, 45. So now let's kind of figure out why. Why are they parallel? Well, think about this. Here's the top and here's the side. And here's another side. If I look at the angle that's formed from the top and the side, it's actually 90 degrees because I took this 45 and this 45. When I add it together, I get 90. And the same thing over here, 45 and 45 gives me 90. So yeah, both the side pieces are perpendicular to the top. And we said two lines perpendicular to the same line are parallel to each other. So let's write that down. Yes, both the side pieces are perpendicular to the top. And we learn the theorem. Two lines perpendicular to the same line are parallel to each other. Remember, we're using our symbol notation, right? This means perpendicular. And this means parallel. We should already know this, but just in case. Okay? So again, if you have to pause and copy this down, but this is how we're going to apply these theorems. All right. So let's continue and see what we have here. So let's try another one. Can you assemble the pieces at the right to form a picture frame with opposite sides parallel and explain? So how can we kind of rearrange what we have here? We have 4 pieces of molding, and we want opposite sides to be parallel. Now, in order to have the opposite sides parallel, we have to think they have to somehow form that 90-degree angle, right? We have to think of how we're going to get 90 degrees. So why don't you kind of pause and think about how can I create 90-degree angles at all 4 corners? And well, you can pause and then replay. And when you play, I will have go over the solution. Okay, so I'm going to start redrawing here. I'm going to take piece 1. Something like this, and I'm going to take piece 2. This is like piece 1. Piece 2, and I'm going to do it something like this. I'm going to take piece 3 and have it go like across like this. And then piece 4, and have it go like this. Okay, so piece 1 had 60 degrees. Piece 2 has 30. Piece 3 has 60. And piece 4 has 30 in the corners. So if you look what we have 60 and 30, which is 90, 60 and 30, which is 90, 30 and 60, 90, 60 and 30 and 90. So we have all 90 degree angles, all right angles. So now we have opposite sides parallel. So basically, as long as 90-degree angles can be formed in all the 4 corners, the opposite sides are going to be parallel. So we know we figured that out. So yes. As long as 90-degree right angles can be formed the opposite sides will be parallel. And we had 30 plus 60 was 90. Check. That happened at all 4 corners. So no, now opposite sides are going to be parallel. Okay, so continuing on with some of these theorems, let's see what we have here. Okay, so this says, in a plane, if a line is perpendicular to one of 2 parallel lines, then it is also perpendicular to the other. Okay, so take a look here. In this picture, we know that L and M are parallel. That's what it says right here. Right, we're telling you that L and N are parallel. N is perpendicular to L. So, since L and M are parallel, right? If N is perpendicular to L, N is also perpendicular to M, right? So what we know here is since N is perpendicular to L, and L is parallel to M, then we know N is also perpendicular to M, right? So L and M are parallel. If N is perpendicular to L, N must also be perpendicular to M. Again, just another theorem. Okay, so now one thing we have to say is that this only happens, right? This whole thought only happens when the lines are in a plane. So if you look at what we have here are just some like statements that I'm gonna kind of put together for you. And we've seen a three-dimensional diagram like this before. Okay, so here we have AC is parallel to BD. Right? Oops, AC is parallel to BD. So if I look at AC and look at BD, they're parallel. They're also in the same plane, like the top. Okay. We also know that EC is perpendicular to AC. So here's EC and here's AC. Now EC and AC are also in the same plane, like the left, right? We know that EC is not perpendicular to BD. So take a look. Although AC is parallel to BD, EC is not perpendicular to BD, even though it's perpendicular to AC, because look at EC and look at BD. They're not even in the same plane. And if you remember about it, since they're not in the same plane, they're actually known as being skew. So not in the same plane, they obviously can't be perpendicular, right? All these, though, separately are in same planes. Okay, so remember, if they're not in the same plane, they can't be perpendicular. They can't even be parallel at that point, right? They're known as skew. Okay, so let's take a look at this. These are fun. I mean, these are known as proofs. I kind of think that they just help us like kind of put things together, work our way through it. Remember, proofs are kind of like proving in the courtroom someone's innocent or someone's guilty, something like that. Okay, so let's take a look at what we have here. In a plane, C is perpendicular to B and B is perpendicular to D. We also know that D is perpendicular to A, and that's all shown right here. We want to prove that C is perpendicular to A. Okay, so let's kind of take two at a time. Let's look here. C is perpendicular to B, and B is perpendicular to D. Okay, so we have C perpendicular to B. D is also perpendicular to B. So what can we then say about C and D? C and D are actually going to be parallel to each other, right? Because two lines perpendicular to the same line, they wind up being parallel to each other. So let's kind of write that out. So we're going to write since C is perpendicular to B and B is perpendicular to D, then C is parallel to D, right? We know this and we can see they're both perpendicular to the same line. And right underneath, I'm just going to write the theorem that kind of justifies that. Two lines perpendicular to the same line means that they are parallel to each other. Okay, make sure you get this down. Okay, so let's see what we can do next. Okay, so now we have to also use that D is perpendicular to A. So let's kind of use D is perpendicular to A, and then D is actually parallel to C. Okay, so let's now take this. So since, what two things do we know? D is perpendicular to A, and D is parallel to C, then, okay, so we know if two lines are parallel, right? These two lines are parallel. Let's say D and C are parallel, but D is perpendicular to A. What could we say about C and A? Right, well, if D and A are perpendicular, but D and C are parallel, well, if D is perpendicular to A, then C must also be perpendicular to A. Oops. So if two lines are parallel, right, and one of those lines is perpendicular to a line, the other must also be perpendicular to that line. Okay, so let's get that down. So, oops. Two are perpendicular. Oops, sorry. Two lines are parallel. Oops. Two lines are parallel. Comma. There we have it, nice and kind of summarized. If two lines are parallel, they are both perpendicular to the same line. So, right, if they're both parallel, if D is perpendicular to A, C must also have to be perpendicular to A. Okay, now in the next section to this, it says, if we think a little bit deeper, could we also conclude that A is parallel to B? So let's think about what we know. How can we prove that A is parallel to B? Now we're given up this information up here, right? We're given these things up here. We're given C is perpendicular to B. We're given B is perpendicular to D. And D is perpendicular to A. I mean, we also know these things. C is parallel to D and C is perpendicular to A. Can we prove that A is parallel to B? Well, I think we can, right? Because we're trying to work with A and B. And if you take a look at these two things right here, I'm going to put them side by side. Or we have that B is perpendicular to D and D is perpendicular to A. Notice that these two, B and A, are both perpendicular to the same line. Well, the theorem states, right, two lines perpendicular to the same line are parallel to each other. So to answer this, yes, we can. Two lines perpendicular to the same line are parallel to each other, like the ceiling and the floor, both being perpendicular to the wall. Those are two planes parallel to the same plane, making them perpendicular to the same plane, making them parallel to each other. So yes, we can. Okay, continuing on. All right, so these are all theorems. Now, we use theorems when dealing with parallel lines. We talked about alternate interior angles. We talked about corresponding angles. We talked about alternate exterior, same side interior angles, everything like that. What we're going to do now is we're going to use parallel lines and their theorems to prove a fact we already know, and not the angles in any triangle, but the angles. In any triangle, sum to what? So if we have a triangle, all three angles add to how many degrees? And the answer is 180 degrees. Right? We already know this. We've talked about this a lot. Now, we actually use parallel lines to prove the triangle angle sum theorem. And this is how it works. So basically, here's our triangle, ABC. Notice we have angle A down here, this angle up here, angle 2, and angle C over here. Now the triangle angle sum theorem basically says that the three angles here, here, and here, so angle A, angle 2, and angle C, those are the three angles of the triangle, they're going to sum to 180 degrees. Right? And we know this fact. We've used this fact, honestly, since middle school. So how do we prove it now? Well, now notice, here we have the bottom of the triangle, and we drew this line up here in. This is actually known as an auxiliary line. I just abbreviate aux line. An auxiliary line sometimes is a line that we draw in to help us out. So now this auxiliary line is drawn parallel to the base of the triangle. Now, anytime you draw lines parallel, all the parallel line theorems come into play. Remember, the parallel line theorems are like alternate interior, alternate exterior, so on and so forth. Now, take a look at what we actually have. Angle 1 and angle A here, these are alternate interior angles. So we know that angle 1 and angle A are equal to each other. So up here, I'm going to put, angle 1. It's actually the measure of angle 1 since we're talking about adding things. So the measure of angle 1 equals the measure of angle A. We also have alternate interior angles over here at C and 3. Measure of angle 3 equals the measure of angle C. We know this because alternate interior angles are equal. Okay. Well, that's all good and fine. But I want to know, how am I getting that A, C, and 2 all add up to 180? And where am I getting 180 from? This is just weird. It's a triangle. How am I getting 180? Now, the 180 comes into play up here. Notice that this is a straight line. And we know when you have a straight line, all the angles that go underneath like that little half circle add up to 180 degrees. Well, there's 3 angles, 1, 2, and 3. So the next thing that I know is the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180. And I know that because angles that form a straight angle sum to 180. All right, well, all good, but I still don't have that A, 2, and C add to 180. But now take a look at what I do have. And I have this. Angle 1 is actually equal to angle A. So if I take out angle 1 right here, I can actually put in angle A. So I'm going to do that. I'm going to do the measure of angle A because 1 and A are the same. Okay, I'm going to leave angle 2 because that's not equal to anything. But over here, angle 3 is actually equal to angle C. So I'm going to take out angle 3 and I'm going to put in angle C since 3 and C are equal. It's known as substitution. Remember we talked about substitution, like for instance, in like a game, right? You have subs. So I'm going to substitute in. I'm going to take out 1 and put in A. I'm going to take out 3 and put in C. So that makes sense. When I substitute or I switched, right? Here and here, I use substitution. And when I use substitution, well, I did exactly what I needed to do. I proved that A, 2, and C, the 3 angles inside this triangle over here, add up to 180 degrees. Okay, now we don't really do this a lot in this class. We don't prove the theorems that we use, but I do find this one to be, kind of relatable because we just talked about parallel line theorems last week and the week before. And then we also are now tying that into triangles. We're going to be working with triangles. Now, this whole thing proves the triangle angle sum theorem, that the 3 angles, the 3 interior angles in any triangle, regardless if it's a right triangle, an obtuse triangle, acute triangle, scalene, isosceles, that doesn't matter. Always, the sum of the measures of the angles inside the triangles will always sum to 180 degrees. And again, just think back in our class, 180 is a really important number, right? Lots of relationships sum to 180. So triangles, you always want to relate 180 to the interior angles of the triangle. Okay, and let's see how we're going to use this theorem up here, right, to try some practice questions. All right, so we're going to try a couple practice questions. And if time runs out, just, obviously wherever we are, we'll stop and we'll pick this up tomorrow during our virtual day. Okay, so let's take a look at number 1. right? Every triangle should have 3 angles, and it does. 1, 2, 3. So this triangle has 3 angles. One of the angles is missing. 1 over here, that's missing. That's not an angle measure, right? Angle measures are shown with degrees. So I know what I know based on what I just told you is that angle 1 plus the other 2 angles, which is 117 and 33, all 3 have to add up to 180 degrees. So once I know that, I can solve for that missing angle. Missing angle is like a variable, right? So now what I can do is I can just use some algebra and I can begin to solve for angle 1. I draw my line down the middle and I begin to combine like terms. Here are my like terms, 117 and 33. So if I add 117 and 33, I get 150. Now don't forget, angle 1 is missing, so I still have to bring that down. Okay, so now I want to get angle 1 by itself. That's like my variable. So in order to do that, I have to subtract 150 from both sides. And 180 minus 150 is 30. So the measure of angle 1, angle 1 measures 30 degrees. So measure angle 1 equals 30 degrees. And you can kind of do a quick check on your head, right? 117 and 33, you just said is 150. 150 and 30 is 180. So that works. Okay, why don't you try to do number 2? So I'm going to put this on pause, or we'll pause the video, figure out how can you use this over here as a little bit of a guide to figure out the measure of angle 1 over here. And then when you're all ready, maybe take a minute or two, play the video, and then you can check your work. Okay, so I would again set up a little equation for myself. I have angle 1 that is missing. And if you want, honestly, you can make this x. Why not? If you don't like using angle 1, that's fine. Okay, so what am I going to do? I'm going to take my 3 angles, 1, 2, 3. I'm going to add them up to 180 degrees. So x plus 44.7 plus 52.2 equals 180. Line down the middle, combine like terms. So I'm going to combine my whole numbers. Here they are. And whole numbers, I should say, my positive values that I have. And I get 96.9 when I add 44.7 and 52.2. Bring down my x plus and my 180. Okay, remember, my line down the middle, if anything has to cross over that line, I have to use the opposite sign. So I'm going to subtract 96.9, subtract 96.9. Come up here. All right, let's see what we have. So these are going to cancel. I have x equals 180 minus 96.9, gives us 83.1. And there you have it. Okay, so x equals 83.1. And that, again, is our final answer. All right, so that's what I'm going to do with the video. If you'd like, you can definitely try to move on and try numbers 3 and 4. We'll definitely go over them tomorrow during the virtual meet. But again, this is really the meat and potatoes of what I want to get through today. So make sure you take your notes home with you and have them with you tomorrow during the meet. Those of you that are at home right now doing this, at least get up through number 2. You can stop, rewind, rewatch whatever you have to, and I will see you all tomorrow. Have a good afternoon.